I'm here to talk about open table formats and Apache Iceberg in particular. That's the one I'm most familiar with. So we'll mostly go with that one. But I think while I'm going to explain what open table formats are, or at least what Apache Iceberg aims to do, I think fairly uniquely, the majority of my talk hopefully is going to focus on what's happening to the data industry, like what is changing and why are open formats what I've been calling, I guess, a quiet revolution. There's a huge transformation happening, and I think we're living through it, but not really realizing what's going on. And it's a very, very big change. So yeah, stay with me. We're going to have some fun. So the story of Apache Iceberg, and I think all of the open table formats in general, goes something like this, where what ended up happening was a whole bunch of distributed systems engineers in the Hadoop days started building what we came to realize eventually was a database. And it's essentially like I love this comic because this is what we did. We essentially used something way too simplistic as a database, and the Hadoop and essentially Hive table format, how we kept track of what data ended up or was in our tables, was just too simple to be successful. And so it was a huge, huge mistake that took years to correct. And that actually led to open table formats. So I'm going to talk about Iceberg's particular origin story in this space. And what basically happened was when I was working for Netflix, where we created Apache Iceberg, we were on Hadoop infrastructure. We were using projects like Spark, like Trino, which was at the time called Presto. We were using Druid. We had a lot of different data systems, all trying to form data architecture, but nothing quite fit together properly. We were plagued by a whole bunch of problems that basically took all of our time and effort. So the first big category of problems was simply correctness issues. In Hive tables and in the Hadoop era, we were plagued by correctness issues because you can't make atomic changes. You can't have ACID transactions or real database transactions if a lot of the state of your table is stored in a file system, which is exactly what Hive does. So Hive would list directories in order to determine which files are currently in the state of a table. And naturally, if you can't make atomic changes to the list of files that are currently in your table, you can't have atomic transactions. And that has a whole huge set of implications that are ugly. So one is, as I'm changing a table, if you're reading it, you might get incorrect results. That's a huge risk. And in fact, it bites many people. Another huge issue is that if you don't trust that other people won't get correct results when you're modifying a table, you never modify a table. You never go back and fix problems. And that, as well as other things, led to cost and performance issues. So cost and performance, if we have, say, the classic example of the small files problem in S3 or HDFS, you're opening and closing too many files to actually, have a very quick read. There are lots of performance implications. And again, if we can't go back and correct it because other people might get incorrect, not just slow results, then that's an issue. And both of these areas, cost and performance and correctness issues, just got way worse at Netflix. When we were at Netflix, we were using S3 as our source of truth, which meant listing files was 10 times slower in terms of latency. It also meant that we had to deal with eventual consistency for listing objects in S3. It was just really, really bad. And that fed into, I think, the main one, which was that data engineering productivity was just incredibly low during the Hadoop era. That was because they either had to, have elaborate workarounds for maintaining tables and providing correctness guarantees. They couldn't rely on even being able to plan queries very quickly on top of S3. And then there were other issues as well, because none of these tables had been designed with SQL guarantees in mind. And we realized that the big picture here was that we weren't able to scale our use of data without increasing or doubling the number of people as the amount of data increased. And it was just a really huge problem, especially in terms of data engineering productivity. What we realized was that all three of these problem areas are linked. They're caused by an overly simplistic way of keeping track of what data constitutes a table, what files are in a table, and how do we make changes to those files. So we went back and said, hey, what if we, instead of taking our distributed systems knowledge and applying it to database problems, what if we tried to learn a lot more from the database world? What if we took a whole bunch of best practices from the database world and started applying those and trying to improve this area? And the result was Apache Iceberg. Now, Iceberg is basically looking at that problem of, how do I view files in an object store as a table? And how do I guarantee that that table has SQL behavior? You might ask, well, why SQL behavior? We get that question a surprising number of times. SQL behavior is important because that is just what people expect. You have people from the data warehousing world. You have people from even the Hadoop world. When you add a column, they have certain expectations. We have 30 years of database research or 50 years of database research going into how should databases behave. And that all goes into the well-known behavior of SQL. So when we created Iceberg and said, we're going to make all of these things work, we're going to solve all of those performance and cost, correctness issues, and data engineering challenges, we said we need to solve all three of those and bring in the database world. So we built a high performance design for S3 to address that cost and performance, where we can actually go and filter out a whole lot more data, and where we can just find data files and what's in our table much more quickly. It's just basically keep a tree structure on top of those files. With that tree structure, we also built full ACID semantics. So you can make atomic changes anywhere in the tree structure that tracks your table metadata, and know that the change is either entirely applied or not applied at all. And we built ways to provide consistency guarantees in the engines that use basically all of those tables. And finally, we also just straight up stole SQL behavior. We made sure that there are no unpleasant surprises with things like performance. If you don't know the physical layout of a table, we made sure there were no unpleasant surprises in like bringing back zombie data from the dead and things like that. And we also took the time to solve problems just to make people productive. So Iceberg includes features like time travel, hidden partitioning, so that you don't have to worry about it on the query side. And it basically solves a lot of problems with unnecessary error-prone patterns. We also have built row-level commands, the high-level, like easy-to-use SQL syntax that you can use to much more easily build declarative patterns like merge, update. And then we also enabled or used the ACID semantics and this idea of data services to build things like automatic compaction and optimization. So Iceberg ends up being a very powerful tool in your arsenal to prevent problems and move forward. Now, let's dive just slightly into SQL behavior. I don't want to go too much into this, but a lot of people think, well, why SQL? And I think this illustrates it quite well. So I have two sets of SQL statements here. Alter table profiles, rename column ID to profile ID. I think it's pretty clear what that should do. And alter table profiles, drop the profile ID column, and add an ID column. Oh, that's actually backwards. It should be renamed profile ID to ID. Or anyway, the question is, should these two things do the same thing, assuming I had profile ID and ID switched here? And the answer is no, of course not. Renames, if I rename my ID column to profile ID, the values in that ID column should still be there. And that's very important because I may need to rename to profile ID, but I don't want to lose the IDs of my table. On the other hand, dropping ID and adding a column profile ID does exactly that. It removes all of those columns and adds a new one. Well, the thing is, in Hiveland, in old Hive tables, these two were the same. They were exactly the same operation. And that was a really big problem because you would lose data when you didn't intend to. You would bring data back from that you thought had been deleted when you didn't intend to. And it was just a big problem. And so one of the things that I think distinguishes Iceberg amongst the table formats was that we always focused on user issues and productivity. And that includes schema evolution. Schema evolution is a part of correctness. And if you get it wrong, it's days worth of headache for data engineers who have to say, oh, right, a rename actually dropped all the data in my table. Now I have to go recover it. And that's a big operation. What if you've written data without that column now? It's a big mess. Similarly, hidden partitioning and other techniques, we wanted to remove this user error that was always associated with partitioning in Hive tables. A writer always has to derive some value to partition by that value, right? Take a timestamp and convert it to a date. Well, what if you use the wrong time zone? What if you use the wrong timestamp? Can we even tell that happened? In fact, there is so much miscategorized data or mispartitioned data in data sets that it's a huge source of correctness problems and data quality concerns even today. And we've had the technology to avoid doing it for a long, long time. So that's a little flavor of what Iceberg attempts to do. And in general, I would, sort of step back up from those two examples and say, the goal of Iceberg is to be invisible. It is to have essentially no unpleasant surprises and not steal attention when it's unnecessary. So unpleasant surprises are things like when you're reading and I'm changing the table, you get wrong information. That's a pretty unpleasant surprise if and when you realize it. Zombie data, another unpleasant surprise. Mysterious performance, unpleasant surprises. But also don't steal attention because at the end of the day, this is a table. Everyone knows how tables should work. So we don't need to have the table involved in every single operation. We don't need analysts to remember, oh, this is how I query some table. So don't make people filter twice. Fix problems without migration. Just fade into the background and let people be productive. So that's what we intended to do with Iceberg. The largest of these is really supporting the behavior and guarantees and reliability of SQL. Now, that brings us to the happy accident. Because what we ended up realizing was that the architecture that we had built at Netflix, where we had Spark and Flink and Trino and other systems all operating on the same tables at the same time. And because we had built ACID semantics, because we had built safe schema evolution and sort of fixed all of the correctness problems in this area, we sort of realized that what we had built with Iceberg went beyond what we initially set out to do. We said, hey, we want to have safe transactions in Spark, Trino, Flink, and other things. And what we'd actually done is opened the door for universal analytic storage, which let me get into what that means a little bit more. Universal analytic storage, as in like we can share database storage underneath these things, right? Spark and Trino are databases. And the assumption of what we were doing was that these two systems that are very, very different can make changes to the same table at the same time. They can query the same table at the same time and have the exact same guarantees as a data warehouse while doing that. And in fact, that's a quick summary of everything that we did in Iceberg, is that we were bringing data warehouse guarantees and reliability and even commands like merge to the data lake space. So this universal analytic storage lens allows us to see sort of why Iceberg is relevant in the data warehouse space, because data warehouses have always been capable of all those guarantees, but not multiple data warehouses, not a data warehouse like Snowflake sharing data with Spark or Trino without copying or moving or doing anything like that. So this really opens the door to universal analytic storage and, more importantly, shared database storage underneath multiple engines. That is actually really, really new, and it has properties that are great for organizations working with data. So number one, you can have one central repository or center of gravity. You don't need to copy data from Snowflake to Redshift or vice versa. You can actually have data sets that are accessible to both at the same time. The next thing is you can bring any compute that you want. You can, or I guess, that's kind of saying the same thing, but it supports batch, it supports streaming, it supports ad hoc, and you can have any client from a Python script all the way through a data warehouse. Now, the weird thing is this is disruptive. So you can imagine that this seems great from the perspective of a user. From the perspective of someone who is a data owner or a platform developer trying to give everyone that we support lots of tools, lots of choice, that's fantastic. But this is actually contrary to the model that most databases use. Almost all databases, through necessity, have never been able to share storage. So the model has been, you put your data in, and then you can access it only through that one engine. You can copy it out maybe, but primarily you access Redshift data through Redshift and Snowflake data through Snowflake. So changing that is unprecedented. Sharing analytic storage underneath data warehouses and data lake engines and anything that you can imagine is actually a quiet, this is what I think of as a quiet revolution. This is something that has never happened before. Storage provides opportunities for performance gains, and being able to share those performance gains or share that storage is very, very odd. Also, tightly coupled storage and compute, like the traditional data warehouse model, creates these natural silos. And those natural silos are there because copying and syncing data is hard. If you want to use some data set through Spark that's stored in Snowflake, how do you do that without copying data? How do you go just test an engine? You have to copy data out. Migrations are risky. So you tend to leave your data in one place and use the only compute engine that can be used on it. So if your data is in Redshift, you tend to use Redshift for things. But now, control of storage is uncertain. Is Redshift going to continue to manage your data even though Spark can access it directly? Is Flink going to manage your data that then Snowflake is going to use? Like, what is going to happen in this space? We honestly don't know. And that's why this is a unprecedented transformation. We don't know where these things are going to end up. But I do think that there's an enormous potential for users. So Iceberg ends up being very disruptive to industry business models. The predominant business model has always been get the user's data and then keep selling compute on top of that data. But now the data is perfectly useful underneath other engines, in place without needing to move it. So it makes workloads really, really easy to move around. And I think we have yet to see exactly the result of that disruption. But I think that we can also start to see some patterns for where the industry is heading with open data formats and make some calls about best practices and how we want to use these. So first of all, I think that this means that data architecture is just becoming more modular. It's going to be the norm, as it was in the data lake space, to be able to use any number of engines, right? You're going to choose where your compute workloads run, and that's not going to be dictated by where the storage resides or where the data is. We're going to have a global S3 or object storage layer, a global table layer on top of that, and then you're going to let engines play in that data as you see fit. I really think that this is going to put you or your organization back in control of your own storage. Modularity is going to depend quite a bit on things fitting together. We need protocols, not just open table standards, but views, catalog standards, authorization like OAuth 2. We need to make sure all of these components fit together without an army of data platformers providing integration and writing small integration config Terraform or whatever. We really need to make sure that all of these engines have open standards to work with one another through. Another principle I think that we're seeing is that we need to secure data and not access points. When data and compute were tightly coupled one-to-one, it was very easy to put the access control enforcement in the compute layer. Well, now that you have 5 or 7 compute layers, how do you secure them? Do you really want to sync access control policy across all of those? I don't think so. And I think that means that access control enforcement needs to move down to the data layer. We need to have things like tabular or lake formation securing the data directly rather than securing the access point. I think it also means that we need more automation services that we've never had in the Hadoop space. And we need to rely more on declarative approaches, telling whatever engine happens to be maintaining the data what to do, not telling a particular engine how to do it. And I want to circle back to the first two. I think the main two principles of modular data architecture and where we're actually headed is you need to be in control of your storage and you need to choose where your compute workloads run. I mentioned a couple slides back that being in control of storage means you're the one creating and defining the opportunities for performance gains. Right. This is very classic, like columnar databases or things that Iceberg and other open table formats do to allow sorting through and filtering out data files that you don't need to read. Storage provides opportunities that engines can then take advantage of. And I think that it's very, very important that you're in control of your storage, because if I'm building an engine and I'm in control of storage, I'm going to make the storage work really well with my engine. It's going to be super fast for the workloads that run on my engine. But that's not necessarily in your interest as the data owner, because you want to use it from batch and ad hoc and streaming. And you don't want, some streaming system, the classic example, to stream data in really easily, but then that data isn't actually prepared for downstream consumption, right? But it is super easy to get it in. So we have these competing interests within the compute space. And I think that the best way for you to ensure that everything works well is if you control your storage and if that storage is actually decoupled from your database vendor. That way you can see, hey, we can optimize this storage and save a whole lot of money on this. Database vendor doesn't necessarily have the incentive or much of an incentive to save you time, save you money, save you the compute credits that you would otherwise be burning on their service. So I think the biggest thing that I would call out about this modular data architecture that is unlocked by open table formats is the need for you to demand neutral or independent storage. And I think that this is actually the big path that the data industry is going on. We're going more towards neutral storage, more towards user controlled or organization owner controlled storage. And of course, independent storage platforms, which happens to be what my company Tabular does. It's a central table store that puts you in control of your storage, plugs into Snowflake, Trino, Flink, Spark, whatever you want to use, and provides access controls and data maintenance to get the best out of those different compute engines. So definitely think about who controls your storage and what you want that to be in the future. And again, this is something where we don't really know how everything is going to end up, but it's a really exciting time and an unprecedented transformation.